we consider a question on complex analysis that has appeared in the National Eligibility Test (NET) will be discussed. It's a question on complex analysis appeared in National Eligibility Test examination held on 26th November 2020 under the section B bearing serial number 34. I will now state the example. For a positive integer p, consider the holomorphic function. Consider the analytic function. F of z is equal to sin z by z to the power of p for non-zero complex numbers z. The question is, for which value of p does there exist a holomorphic function g mapping from non-zero complex numbers to the set of complex numbers such that f of z is equal to the derivative of g of z, that is g prime z, for all non-zero complex numbers z. The options given are: the first option, all even integers; second, all odd integers; third, all multiples of 3; fourth, all multiples of 4. What is the question? For which value of p does there exist a holomorphic function g from the set of non-zero complex numbers to the set of complex numbers such that f of z is equal to the derivative of g of z, that is g prime z, defined for all non-zero complex numbers. Right. Solution. What is given to us? Given p is a positive integer, yes, and f of z is equal to sin z by z to the power of p, which is an analytic function in the set of non-zero complex numbers. Right. Now, f of z is equal to sin z by z to the power of p, and in the we write the Taylor's expansion for sin z 1 by z to the power of p into the expansion of sin z, z minus z cube by 3 factorial plus z to the power of 5 by 5 factorial minus z to the power of 7 by 7 factorial plus etc. And you can take out a z common in this series, and you cancel that z with the one z in the denominator, z to the power of p. So we will do that. That will be equal to 1 by z to the power of p minus 1 into, after taking out z from this series, is 1 minus z square by 3 factorial plus z to the power of 4 by 5 factorial minus z to the power of 6 by 7 factorial, etc. And the we multiply 1 by z to the power of p minus 1, we will take inside the bracket. That will be equal to 1 by z to the power of p minus 1 minus 1 by 3 factorial z to the power of p minus 3 in the denominator only, plus 1 by 5 factorial z to the power of p minus 5 minus 7 factorial 1 by z to the power of p minus 7. So this is your function f of z. We continue in the next slide. So that is the question. We bring forward what is fz from the last slide. F of z is equal to 1 by z to the power of p minus 1 minus 1 by 3 factorial to z to the power of p minus 3 plus 1 by 5 factorial to z to the power of p minus 5 minus 1 by 7 factorial to z to the power of p minus 7 plus so on and so forth. Let gz be such that g prime z is equal to fz. Then if I want gz, integrate on both sides. So the integral of g prime z will be gz is equal to integral of fz. So gz is equal to integral of fz dz. That is equal to the integral of f of z is this one, this series 1 by z to the power of p minus 1 minus 1 by 3 factorial z to the power of p minus 3 plus so on and so forth. So this is coming from the Taylor's expansion, and the term by term integration is valid here. We integrate each term by going into inside the integral. So integral of this will be 1 z to the power of 1 minus p 1 minus p plus 1 by 1 minus p plus 1. That will be equal to 1 by 2 minus p into z to the power of p minus 2 minus in a similar fashion 1 by 3 factorial into 4 minus p into z to the power of p minus 4 plus 1 by 5 factorial into 6 minus p into z to the power of p minus 6 minus etc. Now g of z will be this expansion what we have. If p is an even integer, suppose p is 2, 1 by 2 minus p does not exist. So gz does not exist. Suppose p is 4, this does not exist. So in general, if p is an even integer, then g of z does not exist. G of z does not exist. So therefore, your options 1, that is all even, it holds for all even integers, is false, and all multiples of 4 are even integers only. Therefore this is not true. Therefore options 1 and 4 are not true. Therefore the answer is there in options 2 and 3. We will see that in the next slide. That's the problem and the options. We have g of z is 1 by 2 minus p into z to the power of p minus 2 minus so on and so forth. Let p is equal to an odd integer. P is equal to 2n minus 1, n belongs to n, be any odd integer. Then g of z will be equal to p is 2n minus 1. 2 minus 2n minus 1 will be 3 minus 2n. 1 by 3 minus 2n to z to the power of 2n minus 3. In a similar manner, minus 1 by 3 factorial into 5 minus 2n into z to the power of 2n minus 5 plus 1 by 5 factorial into 7 minus 2n into z to the power of 2n minus 7 minus so on and so forth. Notice that it exists for all n belongs to n. For all n belongs to n, it exists. And it is holomorphic because you can differentiate any number of times. And because it exists for all n belongs to n, it exists for all odd, for any odd positive integer. That means it exists for all odd integers. That is true. And it is a holomorphic function because you can differentiate any number of times. So thus g of z exists for all odd integers p, and therefore the option 2 is true. Because the option 2 is true, the option 3 is not true. Why? All multiples of 3 also contain even integers. That is, for example, 6 is a multiple of 3 and 6 is an even integer. For even integer it does not exist. So therefore now it follows that the option 3 is not true. Therefore our answer is option 2, that it holds good for all odd integers. This comes to the end of the discussion of the question what has appeared on complex analysis in a NET examination. I hope that you have understood the problem and its solution. Now you take some more problems and solve it. All the best. Thank you.